close your eyes or simply let your gaze soften and imagine a mountain. Perhaps it is a peak you have seen with your own eyes, its summit piercing the clouds, or a majestic range etched into your mind from photographs and tales. Feel its immense presence, its silent strength, its ancient, unyielding form. For generations, for centuries, mountains have stood as symbols of permanence, enduring witnesses to the fleeting passage of human lives and civilizations. We look upon them, and they seem utterly immutable, an eternal part of the earth's grand tapestry, unchanging through the ages. Yet this perception, while comforting in its solidity, is but a whisper in the vast echoing halls of geological time. The very concept of eternal begins to dissolve when we gently peel back the veil of millennia, of eons, and allow our minds to stretch beyond the familiar rhythms of days and seasons. The mountains, which appear so steadfast and unwavering, are, in truth, engaged in a slow, graceful, and ceaseless dance. They are not static monuments, but rather dynamic participants in an ongoing planetary ballet, continuously rising, eroding, and reshaping themselves with an elegance that is almost imperceptible to our hurried human senses. This gentle unveiling introduces us to the profound and humbling concept of deep time. A timescale so immense, so vast, that it dwarfs the entirety of human history into a mere blink of an eye. Our own lives, even the longest recorded civilizations, are but ephemeral flickers in the colossal expanse of Earth's existence. When we speak of deep time, we are speaking not in terms of years, or even thousands of years, but in millions and billions of years. It is a concept that asks us to recalibrate our understanding of change, to perceive motion in what appears utterly still, and to find life in what seems undeniably inanimate. Imagine, if you will, a single breath, a slow, deep, calming inhale, and an equally gentle exhale. Now stretch that single breath across 1,000,000 years. The Earth, in its grand planetary existence, breathes in a similar fashion, but on a scale that beggars our comprehension. This gentle breath is the rhythmic expansion and contraction, the subtle shifting and flowing of its mighty crust. It is a living, breathing entity, constantly evolving, perpetually in motion, even as it cradles our existence within its vast and ancient embrace. This is the heart of our journey, to understand this living Earth, not as a rigid, unchanging sphere, but as a dynamic, vibrant world in perpetual transformation. To truly grasp deep time, we must first release our everyday notions of speed and immediacy. Think of a glacier moving at an almost imperceptible crawl, yet possessing the power to carve out valleys and sculpt entire landscapes over thousands of years. Now magnify that slowness, that immense power, by a factor of thousands, and you begin to approach the pace of continental drift and mountain building. The forces at play are not violent or sudden, like a storm or an earthquake. though those too are part of Earth's expressions. Instead, they are forces of immense pressure, unfathomable heat, and relentless patient time, working in concert over epochs. Consider the very stones beneath our feet, the bedrock that forms the foundation of our world. Each grain, each crystal, holds within it a silent chronicle of its own formation, its own journey through time toil. From the fiery depths of the Earth's interior, to the crushing embrace of tectonic plates, to the oil caress of wind and water, these stones have been forged, uplifted, weathered, and reformed. They are not merely inert matter, they are living archives, whispering tales of ancient seas, vanished forests, and mountains that have risen and fallen countless times. This meditative journey invites you to expand your perception, to find stillness in motion and change in permanence. As we delve into the intricate dance of mountains and continents, remember that every peak, every valley, every coastline is a temporary expression of deeper, slower forces. The landscape around us is not a finished painting, but a continuously evolving sculpture, crafted by the patient hand of geological time. There is a profound beauty in this understanding, a sense of wonder in realizing that we are witnesses, however briefly, to a process that has unfolded for billions of years and will continue for billions more. Allow your mind to drift, to imagine the slow, ponderous grinding of colossal landmasses, the gradual accumulation of sediments, the patient uplift of rock layers over unimaginable stretches of time. Envision the Earth as a grand cosmic clock, where each tick of the second hand represents not a single second, but 1,000 years, 1,000,000 years. On such a clock, human history barely registers a flicker, while mountains rise and fall, oceans open and close, and continents embark on their majestic eons-long voyages across the planet's surface. It is a perspective that fosters both humility and a deep connection to the enduring processes of our home world. This is the essence of our exploration into deep time. To perceive the Earth not merely as a stage upon which life unfolds, but as an active, dynamic participant in its own grand narrative. The very ground beneath us is alive, breathing, moving, even as we stand upon it, seemingly unmoving. It is a continuous, slow-motion ballet, where the performers are landmasses of unimaginable size, and the choreography is written by the unseen forces deep within the planet. So, let us embark on this tranquil journey, allowing the vastness of geological time to wash over us, revealing the hidden dynamism of our seemingly static world, and embracing the profound realization that everything, even the mightiest mountain, is a testament to the Earth's gentle, continuous breath. As we continue our gentle descent into the mysteries of our planet, let us now turn our attention from the majestic surfaces we observe to the unseen wonders that lie far beneath. Imagine a journey, not across the land, but straight down, through layers of rock and molten material, deeper and deeper into the Earth's very heart. This is a realm of immense pressure, unimaginable heat, and a constant slow-motion ballet of energy transfer that quietly fuels all the grand transformations we see on the surface. It is here, in the hidden depths, that the true engine of our dynamic Earth resides. Our planet, in its structure, can be likened to a vast spherical fruit, or perhaps a giant onion, composed of distinct concentric layers, each with its own unique characteristics. The outermost layer, the one we stand upon, is the crust, a relatively thin, brittle shell, much like the skin of an apple. Beneath the continents, it can be up to 70 kilometers thick, while under the vast oceans, it thins to a mere 5 to 10 kilometers. This is our familiar world of mountains, valleys, and ocean floors, a delicate veneer floating upon something far more profound and powerful. Below this fragile crust lies the mantle, a colossal layer extending nearly 2,900 kilometers deep. It constitutes the largest volume of the Earth, and it is here that the true magic, the slow-motion engine, begins to churn. While often depicted as molten, the mantle is, in fact, mostly solid, but with a crucial distinction. Under the immense heat and pressure found at these depths, the rock behaves like an extremely viscous plastic material. Think of a very thick, sticky tar, or perhaps a slow-moving caramel. It flows, but over geological timescales, moving with a ponderous grace that is almost unimaginable in our everyday experience. This vast flowing mantle is not uniformly heated. The deeper we descend, the hotter it becomes, primarily due to two powerful sources of heat. Firstly, there is the residual heat from the Earth's very formation, billions of years ago, when our planet coalesced from a swirling cloud of cosmic dust and gas. The sheer energy of this accretion process, the collisions and compressions, generated immense temperatures that have been slowly dissipating ever since. Secondly, and perhaps more importantly, is the continuous decay of radioactive elements within the Earth's interior, such as uranium, thorium, and potassium. These elements, deep within the mantle and core, release thermal energy as they break down, acting like tiny perpetual nuclear reactors, steadily warming the surrounding rock. This continuous generation of heat creates a profound thermal gradient. The core is searingly hot, reaching temperature as it reaches the cooler surface. It cools, becomes denser, and sinks back down, only to be heated again. This continuous circular motion is a convection current, and it is precisely what occurs, albeit on a vastly grander scale and with infinitely greater slowness, within the Earth's mantle. Within the viscous rock of the mantle, plumes of hotter, less dense material slowly rise towards the surface, much like invisible giant balloons. As these plumes ascend, they gradually cool and spread out beneath the rigid crust. In turn, cooler, denser material from near the crust slowly sinks back down towards the core, completing the vast circular flow. These convection currents are immense, slow-moving conveyor belts of rock stretching for thousands of kilometers, their stately pace measured in mere centimeters per year. A speed comparable to the growth of your fingernails. This unseen engine, this vast system of circulating heat and material, is the fundamental power source for all the surface transformations we will explore. It is the silent, immense force that tugs and pushes at the overlying crust, causing it to fracture into massive plates. Without these convection currents, the Earth would be a geologically dead planet, its surface unchanging, its mountains long since eroded flat, its continents fixed in place. But thanks to this inner warmth, this constant, gentle churning, our world remains vibrantly alive, continuously remaking itself from the inside out. Further still, beneath the mantle, lies the Earth's core, a region of incredible density and heat. The outer core, extending from 2,900 to 5,150 kilometers deep, is composed primarily of liquid iron and nickel. The immense temperatures here, reaching over 4,000 to 5,000 degrees Celsius, keep these metals in a molten state. The slow swirling motion of this liquid outer core is responsible for generating Earth's protective magnetic field, a force field that shields us from harmful solar radiation and allows life to flourish. At the very center of our planet, from 5,150 kilometers to the Earth's center at 6,071 kilometers, lies the inner core. Despite even higher temperatures, estimated to be up to 6,000 degrees Celsius, as hot as the sun's surface, the inner core remains solid. This is due to the unimaginable pressure exerted by all the overlying layers, which compacts the iron and nickel atoms so tightly that they cannot melt, even at such extreme temperatures. It is a solid metallic heart, radiating heat outwards, contributing to the mantle's convection and sustaining the Earth's internal dynamism. So, as we emerge from this imagined journey into the Earth's depths, we carry with us a profound understanding. The majestic mountains, the shifting continents, the deep ocean trenches, all are but surface expressions of this grand internal heat engine. The Earth's inner warmth is not merely a passive feature. It is the vital, active force, the quiet breath that sculpts our world, shaping its ancient face with an enduring power that is both immense and serenely slow. It is the unseen heart that beats, ever so gently beneath our feet, driving the great planetary dance. Having journeyed into the Earth's vibrant, active interior, let us now return to the surface, but with the newfound awareness of its underlying dynamism. For many centuries, humanity gazed upon maps of the world, sketching coastlines and charting vast oceans, yet seldom truly questioning the permanence of the landmasses depicted. The continents, like the mountains, were generally perceived as fixed, unmoving features. their shapes immutable since the dawn of time. However, even in those early days, a quiet whisper began to emerge, a subtle hint that perhaps the world was not as static as it seemed. One of the earliest and most striking observations, made by countless map makers and navigators, was the uncanny fit between the coastlines of certain continents. Gaze at a map of the Atlantic Ocean, and you can hardly miss it. The eastern bulge of South America seems to nestle almost perfectly into the western curve of Africa, like two pieces of a colossal jigsaw puzzle. This intriguing geographical coincidence was noted as early as the 16th century by Abraham Ortelius, a Flemish cartographer, who even suggested that the Americas might have been torn away from Europe and Africa by earthquakes and floods. Later, Francis Bacon and Alexander von Humboldt also pondered this remarkable congruence, sensing a deeper connection. These were the first gentle glimmers of an idea that would, much later, revolutionize our understanding of Earth. Yet, for centuries, these observations remained mere curiosities, intriguing patterns on a map without a compelling mechanism to explain them. The prevailing scientific view held that the Earth's crust was rigid and immovable, and any grand shifts in landmasses were simply beyond the realm of scientific possibility. The whispers of a wandering world were there, but they were largely dismissed, awaiting a more robust voice to give them form and substance. That voice arrived in the early 20th century, belonging to a German meteorologist and geophysicist named Alfred Wegener. Fascinated by the continental shapes, Wegener began to meticulously gather a wide array of evidence from disparate scientific fields, seeking to build a coherent case for what he boldly termed continental drift. His hypothesis, first presented in 1912 and elaborated in his seminal book, The Origin of Continents and Oceans in 1915, proposed that all the continents were once joined together in a single supercontinent, which he named Pangaea, meaning all lands. Over vast spans of time, he suggested, this supercontinent had slowly broken apart, and its fragments had drifted across the globe to their present positions. Wegener's genius lay not just in proposing the idea, but in substantiating it with compelling multidisciplinary evidence. Beyond the obvious jigsaw puzzle fit of the continents, he pointed to geological similarities that stretched across vast oceans. For instance, he found remarkable matches in the types and ages of rock formations and mountain ranges on opposite sides of the Atlantic. The ancient Appalachian Mountains of eastern North America, for example, appeared to be a continuation of the Caledonian Mountains in Scotland and Scandinavia, suggesting they were once part of a single continuous mountain belt before the Atlantic Ocean opened up. Even more persuasive was the evidence from fossils. Wegener highlighted the discovery of identical fossil species on continents now separated by thousands of kilometers of ocean. Imagine finding the remains of a small freshwater reptile, Mesosaurus, both in South America and South Africa. This creature was incapable of crossing vast saltwater oceans. Similarly, fossils of the land-dwelling reptile Lystrosaurus and the distinctive fern Glossopteris were found across South America, Africa, India, Antarctica, and Australia. The most logical explanation, Wegener argued, was that these organisms lived on a single landmass that later split apart, carrying their fossilized remains with them. Furthermore, Wegener looked to paleoclimatic evidence, clues about ancient climates preserved in rocks. He observed clear evidence of extensive ancient glaciations in the tropical regions like India, Africa, and South America. These regions, currently warm, bore the unmistakable scars of massive ice sheets, identical to those found in Antarctica. This paradox could only be resolved if these continents were once situated much closer to the South Pole, forming a southern supercontinent called Gondwanaland, before drifting northward to their current warmer latitudes. The glaciers left their telltale marks or striations on rocks, and these patterns, when the continents were reassembled, aligned perfectly, pointing outwards from a central polar location. Despite the elegance and breadth of his evidence, Wegener's hypothesis faced immense skepticism and even ridicule from the scientific community of his time. The primary reason for this rejection was a crucial missing piece: a plausible mechanism. Wegener suggested that continents plowed through the oceanic crust, driven by forces like tidal pull or the centrifugal force of Earth's rotation. Geologists and physicists quickly demonstrated that these forces were far too weak to move entire continents, and that the solid oceanic crust would simply not allow continents to plow through them without immense deformation. Without a convincing how, the idea of wandering continents, no matter how compelling the circumstantial evidence, remained largely an unproven speculation, a beautiful but unsupported whisper. Alfred Wegener died in Greenland in 1930. His revolutionary ideas largely unaccepted during his lifetime. Yet, the seed of his wandering world was planted. It lay dormant for decades, waiting for new technologies and new discoveries to provide the missing pieces of the puzzle. The whispers of continental drift, though quieted by skepticism, never truly faded. They waited patiently, like ancient mountains themselves, for the opportune moment to rise again, stronger and clearer than before, ready to transform our understanding of the Earth's majestic, slow dance. For decades after Alfred Wegener's groundbreaking, yet largely unaccepted theory of continental drift, the scientific world remained largely unconvinced. His brilliant synthesis of evidence, though compelling, lacked one critical component: a mechanism that could explain how colossal land masses might move. The vast, dark, and mysterious ocean floor, covering more than 70% of our planet, held the key to unlocking this puzzle. But its secrets remained profoundly hidden, beyond the reach of early 20th century technology. The oceans were a silent, unexplored frontier, and it was in their depths that the irrefutable proof of a moving Earth would eventually be found. The mid-20th century, particularly the period during and after World War II, ushered in a new era of technological advancement that would dramatically change our understanding of the ocean floor. The development of sonar technology, initially used for submarine detection, allowed scientists to map the topography of the deep seabed with unprecedented detail. Instead of a flat, featureless plain, as many had imagined, the sonar revealed a breathtaking and complex underwater landscape, a hidden heart teeming with dramatic features. Among the most astonishing discoveries were vast continuous underwater mountain ranges, stretching for tens of thousands of kilometers across the globe. These were the mid-ocean ridges, immense chains of volcanoes and rift valleys that snaked through every ocean basin. The Mid-Atlantic Ridge, for instance, runs right down the center of the Atlantic Ocean, mirroring the coastlines of the continents it separates. These ridges were unlike any mountain ranges on land. They were broader, less rugged, and characterized by a central rift valley, almost like a seam running down their spine. Simultaneously, explorers discovered incredibly deep, narrow chasms known as oceanic trenches, often located near continental margins or island arcs. The Mariana Trench, the deepest known point on Earth, plunged to nearly 11 kilometers below the sea surface. These trenches, along with the mid-ocean ridges, presented a planetary puzzle. What geological processes could create such dramatic, contrasting features on the ocean floor? The answers would prove to be revolutionary. Another crucial piece of technology that emerged during this period was the magnetometer, an instrument capable of detecting variations in Earth's magnetic field. When towed behind ships, magnetometers revealed peculiar, striped patterns of magnetic intensity on the ocean floor, particularly parallel to the mid-ocean ridges. These magnetic stripes showed alternating bands of stronger and weaker magnetic signals, arranged symmetrically on either side of the ridge axis. At the time, their significance was not immediately clear, but they were tantalizing clues in the deepening mystery of the ocean's heart. It was the visionary work of Harry Hess, an American geologist and Navy submarine commander, who, in 1960, synthesized these disparate observations into a coherent, groundbreaking hypothesis: seafloor spreading. Hess proposed that the mid-ocean ridges were not merely underwater mountains, but rather sites where new oceanic crust was continuously being created. He theorized that molten rock, or magma, from the Earth's mantle rose up through the rift valleys at the center of the ridges. As this magma erupted and solidified, it formed new oceanic crust, which then slowly moved away from the ridge crests in both directions, much like a giant conveyor belt. To accommodate this constant creation of new crust, Hess suggested that old oceanic crust was simultaneously being consumed elsewhere. He proposed that this occurred at the deep oceanic trenches, where the crust plunged back down into the Earth's mantle, a process he termed subduction. This elegant model provided the long-sought mechanism for continental movement. Continents were not ploughing through the oceanic crust, but rather being passively carried along on these vast, moving conveyor belts of oceanic lithosphere. The real breakthrough in proving sea floor spreading came from combining Hess's ideas with the enigmatic magnetic stripes. In 1963, Fred Vine and Drummond Matthews, building on earlier work by Lawrence Morley, proposed a brilliant explanation for these magnetic anomalies. They hypothesized that as new oceanic crust formed at the mid-ocean ridges, the iron-rich minerals within the solidifying magma would align themselves with Earth's magnetic field at that particular time, much like tiny compass needles freezing in place. They knew that Earth's magnetic field periodically reverses its polarity, meaning that the north magnetic pole becomes the south and vice versa, over periods ranging from thousands to millions of years. Therefore, as new crust continuously formed and spread away from the ridge, it would record a chronological tape recording of these geomagnetic reversals. The alternating bands of stronger and weaker magnetic signals corresponded to periods when the Earth's magnetic field was oriented in its normal direction, as it is today, and periods when it was reversed. This created a symmetrical pattern on either side of the ridge, with identical magnetic stripes mirroring each other across the spreading center. The pattern was a perfect, irrefutable geological barcode, proving that the ocean floor was indeed spreading, and that new crust was continuously being generated at the ridges. Further evidence solidified this theory. Scientists developed techniques to accurately date the age of oceanic crust by analyzing radioactive isotopes in rock samples. They found that the oceanic crust was youngest right at the mid-ocean ridges, and progressively older as one moved further away from the ridges towards the continents and the trenches. The oldest oceanic crust found was only about 200 million years old, remarkably young compared to the continental crust, which can be billions of years old. This confirmed that the ocean floor was indeed a dynamic, constantly renewing surface, being created at ridges and destroyed at trenches, all driven by the powerful convection currents deep within the mantle. The discovery of seafloor spreading and the corroborating evidence from magnetic stripes and crustal dating provided the missing link that finally validated Wegener's vision. Continental drift was no longer a speculative hypothesis. It was more understood as a fundamental part of a larger, more comprehensive theory: plate tectonics. The Earth's surface, it was revealed, is not a solid static shell, but a mosaic of rigid plates, both continental and oceanic, that are in constant, slow motion movement, riding atop the flowing mantle. The oceans, once seen as passive dividers, were now understood as active participants, the dynamic stage upon which the continents embarked on their eons-long journey. The whispers of a wandering world had finally become a resounding chorus, revealing the grand slow dance of continents and the hidden heart that drives them. As our journey through the deep currents of Earth's past continues to unfold, we arrive at a moment of profound understanding, a gentle culmination of all the whispers and hints the planet has offered us through its ancient rocks and shifting seas. It is here, in the quiet contemplation of countless observations, that we begin to piece together the most comprehensive and elegant theory ever conceived to explain the dynamic nature of our world. The grand unifying theory of plate tectonics. This profound realization allows us to view Earth not as a static entity, but as a living, breathing, ever-changing masterpiece, sculpted by forces so immense and so patient that their work unfolds over timescales beyond our everyday comprehension. Imagine, if you will, our vast planet, not as a solid, unmoving sphere, but as a magnificent, ancient mosaic, its surface composed of immense, irregularly shaped tiles. These colossal sections, these silent, majestic pieces of Earth's outermost shell, are what we gently refer to as tectonic plates. They are not merely superficial layers, but deep, substantial segments of the lithosphere, extending downwards from the very surface of the land and the ocean floor, reaching into the warmer, more pliable layers beneath. Each plate is a grand tapestry of both continental crust, with its towering mountains and vast plains, and oceanic crust, with its deep abyssal plains and dramatic ridges, all moving as one cohesive unit. This grand mosaic is not fixed in time or space. No, these plates are engaged in a slow, imperceptible drift, a silent, stately procession across the planet's mantle. Their movement is a continuous, gentle ballet, measured not in footsteps or miles per hour, but in mere centimeters per year. To visualize this, imagine your fingernails growing steadily, quietly, over the course of a year. This gentle, relentless growth is a fitting analogy for the speed at which these immense landmasses journey across the face of our world. Yet, over millions upon millions of years, these tiny, patient movements accumulate into vast migrations, reshaping continents and opening new oceans. The concept of these plates, their boundaries, and their ceaseless motion harmonizes a multitude of previously disparate observations into a single, elegant framework. The distribution of earthquakes, tracing pathways of immense stress release, suddenly makes sense. The patterns of volcanic activity, often forming arcs or lines across the globe, reveal themselves as clear expressions of underlying plate interactions. The enigmatic shapes of continents, like pieces of a grand jigsaw puzzle that once fit together, now find their explanation in the gentle dance of separation and convergence. Even the fossil records, revealing ancient life forms spread across now distant lands, tell a coherent story when viewed through the lens of drifting continents. Each plate, whether it carries the towering peaks of a continent or the silent depths of an ocean basin, is a distinct geographical and geological entity. There are approximately 7 to 8 major plates, vast in their expanse, such as the colossal Pacific Plate, the immense North American Plate, the Eurasian Plate, and the African Plate. These giants dominate the global stage, their slow movements dictating the grand architecture of our planet. Alongside these titans, there are also numerous smaller or minor plates, like the Nazca Plate, the Cocos Plate, and the Philippine Sea Plate. Though smaller in scale, their interactions are no less significant, often leading to intense geological activity in their localized regions. Consider for a moment the sheer scale of these plates. The Pacific Plate, for instance, is largely oceanic, a vast expanse of ocean floor, stretching thousands of kilometers, ringed by a fiery necklace of volcanoes and earthquake zones. It moves with a steady, unyielding momentum, silently interacting with its neighbors. The North American Plate, on the other hand, carries an entire continent from the frigid Arctic to the sun-drenched tropics and extends far out into the Atlantic Ocean. Its western edge is a dynamic boundary, a place of constant subtle tension and occasional dramatic release, while its eastern edge quietly accumulates new crustal material. The driving force behind this colossal, continuous motion is a process of majestic simplicity, yet immense power, originating deep within Earth's interior. We speak of convection currents within the mantle, the vast semi-fluid layer beneath the lithosphere. Imagine a gentle, slow-motion pot of thick, viscous soup heated from below. As the warmer, less dense material rises, it spreads out beneath the surface, then cools and slowly sinks back down. This continuous circular flow acts like a conveyor belt, gently tugging and pushing the overlying tectonic plates. It is a system of immense heat transfer, silently powering the entire global tectonic engine. This deep, internal engine ensures that Earth's surface is never truly still. The plates are perpetually in motion, albeit at speeds that render their journey imperceptible to our fleeting human senses. The continents, those seemingly immutable bastions of stability, are in fact merely passengers on these grand tectonic rafts, slowly migrating across the face of the planet over millions of years. Mountains rise, oceans open, and landmasses fracture and rejoin in an eternal, patient rhythm dictated by these underlying currents. It is a dance of incredible slowness, yet of ultimate power, shaping the world we know in ways both subtle and profound. The boundaries where these plates meet are the true theaters of geological drama. Yet even here, the unfolding events are often measured in millennia rather than moments. These boundaries are the lines on our magnificent mosaic, where the greatest stresses and releases occur, giving rise to the most dramatic surface features. Whether they are gently pulling apart, silently sliding past each other, or engaged in a stately head-on collision, these interactions are the primary architects of Earth's ever-changing face. It is at these edges that the planet expresses its deepest internal energies, creating new land, recycling old, and building the majestic landscapes that inspire wonder. Thus, the theory of plate tectonics offers us a truly grand perspective. It unifies the seemingly chaotic events of earthquakes and volcanoes into a coherent, predictable pattern. It explains the distribution of resources, the evolution of life, and the very geography of our world. It invites us to see Earth not as a collection of isolated phenomena, but as a single, integrated system, where every tremor, every volcanic plume, and every rising mountain range is a direct consequence of the planet's internal warmth and the slow, majestic dance of its outermost shell. As we drift further into the depths of this understanding, we appreciate the profound interconnectedness of all things geological, a testament to Earth's enduring dynamism and its patient, powerful artistry. We are now ready to explore the specific, gentle interactions at these plate boundaries, beginning with the quiet descent of one world beneath another. From the quiet understanding of Earth's grand mosaic, we now turn our gentle gaze to the places where these colossal plates meet, where their slow, inexorable journeys bring them into contact. Among these interactions, one of the most profound and majestic is the process known as subduction, a serene yet immensely powerful dance where one tectonic plate gracefully descends beneath another. This is the place where worlds converge, where the ancient crust of our planet embarks on a silent journey back into the Earth's interior, fueling the gentle rise of new land and shaping the very contours of our oceans and continents. Subduction typically occurs at convergent boundaries, where the paths of two plates lead them towards a head-on embrace. It is a process almost exclusively associated with oceanic crust due to its inherent density. Unlike the lighter, more buoyant continental crust, oceanic crust, rich in heavier minerals like basalt, is naturally denser. As it ages and cools away from the mid-ocean ridges where it was formed, it becomes even more dense, making it prone to sinking when it encounters another plate. This gentle downward pull, driven by gravity and the weight of the cooling rock, is the quiet engine of subduction. Imagine two vast, flat rafts slowly drifting towards each other across an immense, calm sea. As they meet, one raft, being slightly heavier, begins to slide silently beneath the other, disappearing beneath the surface. This is the essence of subduction. The descending oceanic plate, often tens of kilometers thick, begins its immense, slow dive into the warmer, more pliable mantle below, a journey that can extend hundreds of kilometers into Earth's depths. This descent is not a violent plunge, but a gradual, stately inclination, a continuous, unhurried sinking that unfolds over millions of years. As the oceanic plate begins its downward journey, the immense pressure and friction between the two converging plates create a distinctive and profound feature on the ocean floor: the deep ocean trench. These trenches are the deepest parts of our planet's oceans. Long, narrow depressions that plunge to astonishing depths, far greater than the average ocean floor. They are the silent witnesses to the Earth's recycling process, marking the precise line where one plate begins its slow descent. The Mariana Trench, the deepest known point on Earth, a majestic chasm nearly 11 kilometers deep, is a prime example of such a feature, a testament to the immense forces at play in subduction. These trenches are not merely passive depressions. They are dynamic zones where the descending plate scrapes against the overriding plate, causing the release of immense stress in the form of deep earthquakes. Yet, even these powerful seismic events are part of the larger calm flow of Earth's processes, merely moments of release within an eons-long ballet. As the oceanic plate continues its descent, it carries with it trapped water and volatile compounds, which are slowly released into the overlying mantle rock as the plate heats up. This infusion of volatiles lowers the melting point of the mantle rock, causing it to partially melt and form magma. This newly formed magma, being less dense than the surrounding solid rock, begins a slow, buoyant ascent towards the surface. It is a gentle, unhurried migration upwards, pushing its way through cracks and fissures in the overriding plate. Over millions of years, this persistent, upward flow of magma leads to the serene rise of volcanic activity on the surface. The nature of this volcanic expression depends on whether the overriding plate is oceanic or continental. When two oceanic plates converge and one subducts beneath the other, the rising magma breaks through the overriding oceanic crust to form a chain of volcanoes on the ocean floor. Over vast stretches of time, as more magma erupts and solidifies, these underwater volcanoes grow taller and taller, eventually emerging above the ocean surface as a majestic arc of volcanic islands. These are known as volcanic island arcs, tranquil chains of islands, often curved in shape, that parallel the deep ocean trench from which they are born. The gentle beauty of the Japanese archipelago, the Aleutian Islands, and the islands of Indonesia are all serene manifestations of this profound oceanic subduction. These island arcs are not sudden creations. They are the cumulative result of millions of years of patient magmatic activity, each eruption adding another gentle layer to their growth. Their volcanic peaks often slumber for long periods, only occasionally stirring to release their internal energies in a measured, powerful way. The quiet beauty of their landscapes, with fertile volcanic soils and dramatic coastlines, speaks to the immense, slow forces that brought them into being, a serene reminder of the Earth's continuous renewal. A different, yet equally majestic scenario unfolds when an oceanic plate encounters a continental plate. Here, the denser oceanic plate unfailingly subducts beneath the lighter, more buoyant continental plate. The process begins similarly, with the formation of a deep ocean trench just offshore of the continent. This trench marks the boundary where the oceanic crust begins its silent dive beneath the continental margin. A continuous line of deep water paralleling the coast. As the oceanic plate descends beneath the continent, the same process of heating, dehydration, and magma generation occurs. The rising magma then penetrates the thick, ancient continental crust. This magma, often more viscous and gas-rich after its journey through the continental rock, fuels the rise of magnificent volcanic mountain ranges along the continental edge. These are the majestic coastal mountain ranges. Their peaks often crowned with snow, their slopes carved by ancient glaciers. Their very existence a testament to the patient power of subduction. The Andes Mountains in South America, stretching thousands of kilometers along the western edge of the continent, are a breathtaking example of such a process. Here, the Nazca Plate is slowly, relentlessly subducting beneath the South American plate, a dance that has been unfolding for tens of millions of years. This immense, continuous pressure and the relentless upward push of magma have sculpted a range of unparalleled grandeur, a majestic backbone for a continent. The volcanoes dotting the Andes, some active, some dormant, are the gentle breath of this ongoing geological process, silent sentinels watching over the land. Beyond the volcanic activity, the subduction of an oceanic plate beneath a continent also contributes to the uplift and deformation of the overriding continental crust. The immense lateral pressure of the converging plates, combined with the buoyant rise of magma, causes the continental edge to fold, fault, and thicken. This gentle squeezing and lifting over eons contributes significantly to the overall height and ruggedness of these coastal mountain ranges, creating landscapes of dramatic beauty and profound geological history. Thus, the dance of subduction is a cornerstone of Earth's dynamic system. It is the primary mechanism for recycling old oceanic crust, returning it to the mantle from whence it came. It is the engine that drives the creation of deep ocean trenches, the planet's deepest abysses, and most serenely, it is the silent artisan behind the majestic volcanic island arcs and the towering coastal mountain ranges that grace our planet's surface. In this gentle, unhurried descent, we witness the profound interconnectedness of Earth's processes, a continuous cycle of creation, transformation, and renewal, all unfolding with a tranquil grace over immense spans of geological time. As we reflect on this quiet descent, we are prepared to witness an even more profound act of creation, the collision of continents themselves. Having observed the graceful descent of oceanic plates in the dance of subduction, our journey through Earth's deep time now brings us to perhaps the most awe-inspiring act of terrestrial creation, the slow, powerful collision of two continental plates. This is where the true giants of our planet are born, where the Earth itself seems to arch its back and slowly push towards the heavens, creating the grandest mountain ranges, monuments of immense pressure and unimaginable patience. This silent, stately process unfolds over millions of years, transforming vast flatlands into towering peaks, a testament to the planet's enduring power. Unlike oceanic crust, which is dense and readily sinks back into the mantle, continental crust is inherently buoyant, like a vast unyielding raft. It is simply too light to be subducted deep into the Earth's interior. So when an ocean basin that once separated two continental plates finally closes through the process of subduction, the stage is set for a monumental confrontation. The oceanic crust between them is consumed, slowly, over eons, until the two continental masses finally make contact. This initial gentle touch marks the beginning of a profound and prolonged struggle, a collision of unparalleled geological significance. Imagine two colossal ancient landmasses, each carrying the weight of billions of years of history, slowly, inexorably drifting towards each other. Their journey is measured in mere centimeters per year, a pace so slow it is utterly imperceptible to our fleeting human existence. Yet, this gentle, relentless pressure, sustained over tens of millions of years, accumulates into a force beyond human comprehension. When these vast continental plates finally meet, there is no subduction in the typical sense. Instead, the crust begins to buckle, to fold, to fracture, and to be pushed upwards, forming new immense mountain chains. This collision is not a sudden, violent impact, but rather a slow, grinding embrace, an eons-long compression. The immense lateral forces exerted by the colliding plates cause the thick continental crust to shorten and thicken significantly. This shortening is accommodated through several majestic processes. Firstly, the rocks are subjected to incredible compressive stress, causing them to deform plastically, much like a thick rug being pushed from opposite ends. This results in the formation of magnificent folds, where layers of rock are bent and warped into sweeping arches, anticlines and troughs, synclines, visible in the layered patterns of mountain faces. Secondly, where the rocks cannot bend further, they fracture and break along immense fault lines. These are not small cracks, but vast ruptures that can extend for hundreds of kilometers. In a continental collision, a particularly common type of fault is a thrust fault, where one block of crust is pushed up and over another. Imagine an entire section of Earth's surface being gently, slowly lifted and slid horizontally over another section, creating immense sheets of rock stacked upon one another. This stacking, this imbrication of crustal slices, significantly increases the thickness of the continental crust, contributing directly to the vertical growth of the mountains. It is this combination of intense folding and extensive faulting, driven by the relentless slow-motion squeeze of two continents, that leads to the majestic uplift of the Earth's grandest mountain ranges. The process is one of continuous elevation, where the land literally rises inch by painstaking inch, year after year, for millions upon millions of years. The weight of the overlying rock, combined with the heat from below, further deforms the deeper crust, making it more ductile and prone to flow, contributing to the overall thickening and upward movement. The most iconic and breathtaking example of this profound process is the formation of the Himalayas, the highest mountain range on Earth, home to Mount Everest, the world's tallest peak. This majestic range is the direct result of the ongoing collision between the Indian plate and the Eurasian plate. Approximately 50 to 60 million years ago, the Indian subcontinent, which had been drifting northwards for millions of years, after breaking away from the ancient supercontinent of Gondwana, finally made contact with the southern edge of Asia. Before the collision, a vast ocean, the ancient Tethys Sea, separated these two landmasses. As the Indian plate drifted north, this oceanic crust was gradually subducted beneath the Eurasian plate. But once the buoyant continental crust of India met Asia, subduction ceased, and the immense, unyielding squeeze began. Imagine two immovable objects, each pushing against the other with the entire force of a continental plate. The Tethys Sea and the sediments accumulated within it were violently crumpled, folded, and uplifted, forming the initial foothills of what would become the Himalayas. But the collision did not stop there. It continues even to this very day. The Indian plate is still slowly, relentlessly pushing northward into the Eurasian plate, at a rate of several centimeters per year. This continuous pressure is what fuels the ongoing uplift of the Himalayas, making them one of the most geologically active and rapidly rising mountain ranges on the planet. The majestic peaks we see today are literally being pushed higher, millimeter by millimeter, a silent, perpetual struggle against the forces of erosion that constantly try to wear them down. Within the Himalayas, one can observe evidence of this titanic struggle everywhere. Ancient marine fossils, remnants of the Tethys Sea, can be found high in the mountains, a silent testament to the oceanic origins of some of the rocks now thousands of meters above sea level. The incredibly complex geology, with its intricate folds, thrust faults, and metamorphosed rocks, tells a story of intense heat, pressure, and deformation on a scale that is truly humbling. The sheer volume of rock that has been uplifted is staggering, forming a vast, elevated plateau that profoundly influences global climate patterns. Other majestic mountain ranges around the world are also products of similar continental collisions. The Alps in Europe, for instance, are the result of the collision between the African plate and the Eurasian plate. The Urals, which divide Europe and Asia, represent an even older collision, a faded scar on the Earth's surface from a supercontinent assembly in the distant past. Each of these ranges, in its own unique way, tells a story of two worlds embracing in a slow, powerful dance, their crusts crumpling and rising to form magnificent natural cathedrals. The birth of giants through continental collision is a process of immense beauty and profound geological significance. It is a slow, patient, drawn act of creation, unfolding over timescales that stretch the imagination. The mountains born from these collisions are not merely static features. They are dynamic landscapes, constantly being shaped by the ongoing tectonic forces and the relentless work of erosion. They stand as silent, majestic reminders of the Earth's deep internal power, its ability to reshape itself in the most dramatic ways, yet always with a gentle, unhurried pace. As we contemplate the enduring power of these continental embraces, we prepare to explore the more gentle separations and silent glides that also continuously sculpt our world. Having marveled at the slow, powerful embrace of continental collisions and the majestic descent of subduction zones, our meditative journey through Earth's tectonic ballet now guides us to observe the other graceful movements of our planet's colossal plates. Here we will witness the quiet beauty of creation, where plates gently pull apart, giving birth to new crust, and the silent, transformative glides where they slide past each other, reshaping the land with subtle yet profound energy. These are the processes of divergence and shear, completing the continuous cycle of transformation that sculpts our ancient Earth. Let us first turn our attention to the gentle separations, the divergent plate boundaries, where the Earth's crust is not compressed or consumed, but rather stretched and renewed. Imagine a vast underlying force gently pulling two adjacent tectonic plates away from each other. This is not a sudden, violent tearing, but a slow, continuous stretching and thinning of the lithosphere over immense spans of time. As the plates move apart, the pressure on the underlying mantle is reduced, allowing the warmer, more pliable material from deep within the Earth to rise slowly towards the surface. This rising mantle material then partially melts due to the decrease in pressure, forming new magma. This magma, buoyant and persistent, gently ascends to fill the gap created by the separating plates. As it reaches the surface, it erupts and solidifies, forming new oceanic crust. This continuous process of magma rising, solidifying, and pushing the plates further apart is the serene engine behind the creation of mid-ocean ridges. These majestic underwater mountain ranges are the longest mountain chains on Earth, stretching for tens of thousands of kilometers across the floors of our great oceans, a testament to the planet's continuous renewal. The Mid-Atlantic Ridge, for example, is a colossal underwater backbone, quietly adding new crust to both the North American and Eurasian plates and the South American and African plates, pushing them gently apart. At the crest of these mid-ocean ridges lies a central rift valley, a deep, narrow trench that marks the very point of separation. It is here that the freshest, youngest oceanic crust is formed, a continuous ribbon of new rock emerging from the Earth's interior. As new magma wells up and solidifies, it slowly pushes the previously formed crust away from the ridge axis, much like a slow-motion conveyor belt. This process, known as seafloor spreading, is the fundamental mechanism of plate tectonics, constantly generating new ocean floor and slowly expanding the ocean basins. The age of the oceanic crust systematically increases with the distance from the ridge, a silent geological clock marking the passage of eons. These divergent boundaries are not confined solely to the ocean depths. Sometimes, the forces of divergence begin to pull apart a continental landmass, leading to the formation of a continental rift valley. Here, the continental crust is stretched, thinned, and fractured into a series of parallel faults. As the crust thins, blocks of land subside, creating a valley flanked by uplifted shoulders. Magma often rises along these faults, leading to volcanic activity and the slow, patient splitting of a continent. The East African Rift Valley is a magnificent example of this process. A vast, slowly widening system of valleys and volcanoes that will, over tens of millions of years, eventually lead to the formation of a new ocean basin, gently separating Eastern Africa from the rest of the continent. The creation of new crust at divergent boundaries is a continuous, quiet process of growth and expansion. It balances the consumption of old crust at subduction zones, maintaining a dynamic equilibrium on our planet. It is a testament to Earth's ability to constantly renew its surface, a gentle, creative force that shapes the vast, unseen landscapes beneath our oceans and slowly reconfigures the continents we inhabit. The heat escaping from the Earth's interior at these boundaries creates unique hydrothermal vent ecosystems, teeming with life, adapt to conditions of extreme pressure and temperature, a vibrant oasis in the deep, dark ocean, all born from the gentle separation of worlds. Now, let us shift our meditative focus to the third major type of plate interaction. The silent, transformative glide of plates past each other along transform faults. Here, plates neither converge to create or consume crust, nor diverge to form new crust. Instead, they move horizontally, side by side in opposite directions, or in the same direction at different speeds. Imagine two immense, flat surfaces slowly scraping past each other, generating friction and stress along their shared boundary. This movement is a continuous shear, a quiet, grinding motion that can reshape coastlines and influence the distribution of earthquakes. Transform faults are often found connecting segments of mid-ocean ridges, where they offset the ridge axis. However, some of the most dramatic and well-known transform faults occur within continental crust, where their silent lateral movement has profound effects on the landscape. The most famous example is the San Andreas Fault in California, a vast linear scar on the Earth's surface that stretches for over 1,300 kilometers. Along this immense fault, the Pacific Plate is slowly, patiently sliding northwestward past the North American Plate. This movement is not smooth and continuous. Instead, immense stress builds up along the fault as the two plates try to move past each other. The rocks are essentially locked in place by friction for long periods, accumulating elastic energy. When this stress eventually overcomes the friction, the rocks suddenly slip, releasing the accumulated energy in the form of an earthquake. These events, though sometimes powerful, are merely moments of release within the ongoing silent glide of the plates. A reset in the continuous slow-motion movement. The quiet accumulation of stress over decades or centuries is then released in a matter of seconds, only for the slow process to begin anew. Over millions of years, this continuous, silent gliding along transform faults profoundly reshapes the landscape. Rivers are offset, mountain ranges are sliced and separated, and features that were once continuous are slowly pulled apart. The San Andreas Fault, for instance, has dramatically altered the topography of California, creating linear valleys and influencing the distribution of different rock types across the region. It is a testament to the cumulative power of small, continuous movements, silently working over vast timescales to transform the very face of the land. These transformative glides are not destructive in the same sense as a major collision, nor are they overtly creative like a divergent boundary. Instead, they are zones of continuous quiet rearrangement, slowly shuffling the pieces of Earth's tectonic mosaic. They are essential components of the global plate tectonic system, accommodating the differential movements of plates and ensuring the smooth, albeit sometimes punctuated, flow of the Earth's surface. In observing these gentle separations and transformative glides, we complete our understanding of the fundamental ways in which Earth's tectonic plates interact. We have seen how divergence creates new crust and expands oceans, how subduction recycles old crust and builds volcanic arcs and coastal mountains, and how continental collisions raise the grandest mountain ranges. And now, we understand the silent, lateral movements of transform faults that accommodate these grand forces. Each process, whether a gentle pull, a quiet descent, a powerful embrace, or a silent glide, is part of a continuous, interconnected cycle of creation and quiet transformation across our planet. This understanding reveals a truly dynamic Earth, a world where nothing is truly static, where every landscape, every ocean, and every mountain range is a fleeting stage in an eons-long drama. The forces are immense, the timescales vast, but the underlying rhythm is one of patient, continuous change, a tranquil dance orchestrated by the planet's internal warmth. As we conclude this segment, we carry with us the profound appreciation for the gentle yet powerful forces that continuously reshape Earth's ancient, ever-evolving face, inviting us to find peace in the planet's enduring dynamism. Let us now gently broaden our gaze, expanding our journey through deep time to encompass even grander, slower cycles. We have observed the steady march of continents and the patient rise of mountain ranges. But these are merely notes in a much longer, more profound symphony. Imagine, if you will, the earth itself breathing, its great landmasses not merely drifting apart or colliding, but performing an eons-long dance of assembly and dispersal, forming colossal supercontinents that dominate the planet's face for hundreds of millions of years, only to fracture and begin the slow, deliberate process anew. This is the story of supercontinents, a rhythm so ancient and vast that it dwarfs even the most colossal mountain ranges in its scope. It speaks to an enduring cycle, a fundamental heartbeat of our planet, where the continents coalesce into a single magnificent landmass, then slowly and inexorably pull apart, scattering across the globe before, in the unfathomable future, beginning their slow gravitational pull back towards one another. It is a testament to the ceaseless energy within Earth, a perpetual renewal played out on the grandest possible stage. The most famous of these immense landmasses, one that perhaps lingers most vividly in our collective imagination, is Pangaea. Its name, derived from ancient Greek, simply means all lands, a perfect descriptor for a continent that united nearly all the Earth's continental crust into a single awe-inspiring entity. If we could gaze down from the silent reaches of the cosmos some 335 million years ago, we would have witnessed a sight profoundly different from the scattered continents we know today. A solitary, sprawling behemoth, an almost unbroken expanse of land dominating one hemisphere, while the rest of the planet was covered by a single, immense global ocean known as Panthalassa. Pangaea was not born overnight, nor in a single cataclysmic event. Its formation was the culmination of an earlier supercontinent cycle, a slow, deliberate process of continental collisions that spanned tens of millions of years. It was the result of multiple ancient continents, themselves fragments of even older landmasses, slowly converging, their edges grinding and folding against one another with unimaginable pressure. The ancient mountain ranges we touched upon earlier, such as the distant ancestors of the Appalachians in North America and the Urals in Eurasia, stand today as the eroded remnants of these colossal stitching events, monuments to the forces that welded Pangaea together. Imagine the world during Pangaea's reign. The vast interior of this supercontinent would have experienced extreme climates, far from the moderating influence of the ocean. Enormous deserts would have stretched across its heart, scorching by day and freezing by night, while coastal regions might have enjoyed more temperate conditions. Life, too, adapted to this unique global configuration. Early reptiles, precursors to the dinosaurs, roamed freely across what would one day become vastly separate continents, their fossil remains offering silent testimony to Pangaea's once unified landmass. Vast fern forests and early conifer trees thrived, creating ecosystems that spanned latitudes and longitudes we now associate with entirely different parts of the world. But even a landmass as monumental as Pangaea was not destined to last forever. The very forces that brought it together eventually began to pull it apart. Around 175 million years ago, the Earth's restless mantle began to stir with renewed vigor beneath Pangaea's colossal weight. Plumes of superheated rock began to rise from the deep, stretching and thinning the continental crust above. This slow, inexorable tension initiated a process known as rifting, where the vast supercontinent began to crack and tear along immense fault lines, much like ice fracturing on a frozen lake, but on a geological scale of unimaginable slowness. The initial split saw Pangaea divide into two major landmasses: Laurasia to the north, which would eventually become North America and Eurasia, and Gondwana to the south, the ancient ancestor of South America, Africa, Antarctica, Australia, and India. Between them, a new ocean basin began to open, the nascent Tethys Sea, a precursor to the Mediterranean. As the rifting continued, magma welled up from beneath, solidifying to form new oceanic crust, slowly pushing the nascent continents further and further apart. This was the birth of the Atlantic Ocean, a vast expanse that has been steadily widening ever since, pushing the Americas westward and Eurasia and Africa eastward. The breakup of Gondwana itself was a series of further, equally patient rifting events. South America separated from Africa. India began its long, solitary journey northward towards Asia, and Australia embarked on its drift towards the equator. Each separation was marked by the formation of new ocean basins, each tearing apart a shared biological heritage, setting species on independent evolutionary paths. This grand, slow dismemberment profoundly reshaped the planet's geography, climate, and the very course of life on Earth. Yet, Pangaea was not the first supercontinent, nor will it be the last. The geological record, inscribed in ancient rocks and mountain belts, reveals a recurring pattern, a profound rhythm known as the supercontinent cycle or the Wilson cycle. This cycle describes the episodic opening and closing of ocean basins, driven by the relentless forces of plate tectonics, which ultimately leads to the periodic assembly and breakup of supercontinents. It's a dance that has been unfolding for billions of years, a testament to the Earth's enduring dynamism. Before Pangaea, there was Rodinia, a supercontinent that formed approximately 1 billion years ago and began to break apart around 750 million years ago. Its breakup is believed to have played a significant role in triggering some of Earth's most extreme ice ages, the Snowball Earth events, by influencing ocean currents and atmospheric carbon dioxide levels. And before Rodinia, geologists have identified evidence for even older supercontinents, such as Columbia, also known as Nuna, which existed between 1.8 and 1.5 billion years ago, and perhaps even Valbara, a very early supercontinent, speculated to have formed as far back as 3.6 to 2.8 billion years ago. These ancient names whispered by the rocks remind us that Pangaea was but one chapter in an infinitely longer story. The mechanism behind this grand cycle is deeply intertwined with the processes we've already explored. It begins with continents rifting apart, forming new ocean basins as magma rises at mid-ocean ridges. These oceans widen for tens of millions of years, creating vast expanses of new oceanic crust. Eventually, however, the heavy, cooling oceanic crust begins to subduct beneath lighter continental crust, or other oceanic plates, forming deep ocean trenches and consuming the very ocean that was created. As these oceans slowly shrink, the continents on either side are drawn inexorably towards one another, ultimately colliding with immense force to form new mountain ranges and eventually a new supercontinent. Then the cycle begins anew, a patient, never-ending ebb and flow of continental masses. This enduring cycle profoundly impacts nearly every aspect of our planet. Supercontinents create extreme continental climates with vast, arid interiors and unique patterns of ocean circulation. Their breakup leads to fragmentation, creating more moderate maritime climates, altering global sea levels as mid-ocean ridges become more active and displace more water, and fostering an explosion of biodiversity as species become isolated on separate land masses, evolving along divergent paths. Even the distribution of Earth's mineral wealth, from precious metals to fossil fuels, is intimately linked to the tectonic events and climatic conditions associated with these supercontinent cycles. To contemplate these supercontinent cycles is to gain a profound appreciation for the Earth's deep past and its enduring cyclical nature. It is a revelation that the land beneath our feet is not merely moving, but participating in an ancient grand ballet, a cosmic dance of assembly and dispersal that has shaped our world for billions of years. This rhythm of ages, slow and unhurried, offers a sense of deep calm, a recognition that the planet operates on timescales far beyond our comprehension, yet with a predictable elegance that brings a quiet peace to the restless human mind. It is a reminder that the Earth is a self-renewing system, constantly evolving, constantly reshaping itself through processes that are as gentle in their unfolding as they are powerful in their ultimate effect. The quiet hum of geological time continues, carrying continents on its vast, patient currents. As our tranquil journey through deep time draws to a close, we find ourselves not at an end, but at a pause, a moment of reflection on an ongoing narrative. The story of mountains and plate tectonics is not a finished tale, neatly bound and put upon a shelf. Rather, it is an epic poem still being written, its verses unfolding with unimaginable slowness, each day adding a new, imperceptible line to the Earth's majestic chronicle. We understand now that our planet is a perpetually evolving canvas, a dynamic masterpiece under continuous, gentle revision by the very forces we have come to appreciate. The dance of continents, though silent and unseen by the fleeting human eye, continues its stately procession in this very moment. North America continues its patient westward drift, slowly widening the Atlantic Ocean by a few centimeters each year. The Pacific Ocean, in turn, continues its slow contraction, its edges being consumed beneath the surrounding continental plates in the deep recycling embrace of subduction zones. The African continent continues its northward trajectory, gradually narrowing the Mediterranean Sea, an ancient ocean basin destined, in the deep future, to close entirely. These movements, subtle as they are on our human timescale, are relentless, a constant quiet hum of geological activity beneath our feet. Even the mountains we have observed, rising with such patient majesty, are still in motion, their upward thrust a testament to the ongoing collisions and uplift. The Himalayas, those towering giants born from the collision of India and Asia, continue their slow ascent, growing by millimeters each year. The Andes, a grand spine along the western edge of South America, are still being sculpted by the subduction of the Nazca Plate beneath the continent. These peaks are not static monuments, but living landforms, actively participating in the Earth's grand geological ballet, their very existence a symbol of the planet's enduring vitality. But creation is only one half of Earth's eternal rhythm. For every mountain that rises, there are forces patiently working to wear it down. This is the gentle hand of erosion, a quiet, pervasive sculptor that tirelessly shapes the surface of our world. Wind, water, ice, and gravity, working in concert over millions of years, slowly chip away at the hardest rock, transforming jagged peaks into rolling hills and eventually into vast flat plains. Imagine a mighty mountain range born of immense tectonic power, slowly, patiently softening its edges, its sharp angles smoothed by the ceaseless caress of rain and the grinding passage of glaciers, its substance carried grain by grain to lower elevations. Water, in its myriad forms, is perhaps the most persistent of these sculptors. Rivers tirelessly carve valleys, carrying sediments from the highest peaks to the lowest basins, eventually depositing them in lakes, more often vast deltas leading into the oceans. Rain, a gentle patter on our windows, becomes a powerful agent of change over geological time, dissolving minerals and washing away loose soil. Ice in the form of glaciers acts as an immense slow-moving bulldozer, grinding down mountainsides and carving out U-shaped valleys, leaving behind distinct glacial landscapes that speak of ancient, colder eras. These processes of wearing down, though seemingly destructive, are integral to the Earth's continuous renewal. The sediments carried away by erosion do not simply disappear. They embark on their own long journey, becoming the raw material for the next phase of Earth's transformation. The rock cycle, These grains of sand, silt and clay, once part of a towering mountain, are deposited layer upon layer, slowly compacting and cementing together over millions of years to form new sedimentary rocks. Buried deeper still, subjected to immense heat and pressure, these sedimentary rocks can be transformed into metamorphic rocks, their very structure and mineral composition altered by the subterranean crucible. And should they be drawn even deeper into the Earth's mantle, they might melt entirely, becoming magma, only to rise again and cool, forming new igneous rocks, perhaps destined to be uplifted once more, beginning the cycle anew. This continuous loop, from mountain to sediment, from rock to magma and back again, illustrates the profound interconnectedness of all Earth's processes. It is a seamless, elegant cycle, driven by the internal heat of the planet and sculpted by the external forces of weather and gravity. It is a testament to the Earth's self-regulating nature, a system of perpetual recycling and renewal that has sustained our planet for billions of years. There is a deep, quiet assurance in this understanding, a sense of belonging to something so vast and enduring. And what of the future? The story, as we've established, continues. Millions of years from now, the Earth's map will look profoundly different. The Atlantic Ocean will likely continue to widen, while the Pacific Ocean will continue to shrink. Africa, in its northward push, will ultimately collide with Europe, raising a new colossal mountain range and perhaps eliminating the Mediterranean Sea entirely. Australia will likely continue its journey north, eventually colliding with Asia. And in the very distant future, perhaps 250 to 300 million years from now, the continents may once again converge to form a new supercontinent, perhaps dubbed Pangaea Ultima or Amasya, a monumental landmass that will once again reshape global climates and the course of evolution. This is not mere speculation, but a gentle projection based on the enduring, predictable rhythms of plate tectonics. To contemplate such vast timescales, to envision the Earth's ceaseless transformation into an unimaginable future brings a profound sense of peace. Our human lives, vibrant and meaningful as they are but a fleeting breath in the grand cosmic year of our planet. The Earth, however, operates on eons, on a scale of patience that we can only humbly observe and admire. It is not rushed, not hurried, but moves with an inherent, unyielding grace, continually creating, continually transforming. In this understanding, we find a deep, abiding calm, the continuous cycle of creation and destruction, of uplift and erosion, of continental assembly and dispersal, is not a chaotic process, but a rhythmic, beautiful dance. It is the Earth's eternal lullaby, a quiet song of change that has played out for billions of years and will continue to play for billions more. We are privileged to be witnesses, however brief, to this magnificent spectacle. May the profound peace of the Earth's eternal patient transformation settle upon you, a gentle reminder of the enduring beauty and quiet power of our planetary home. Rest now in the vast, patient rhythm of the Earth.